5.6. Connecting variation, slope, and first differences. The following table shows the height compared to the ground of a snail crawling up a pipe. You'll notice that the time in minutes and the height in meters. So at 0 minutes, the height of the snail was -3 meters. That would mean that the snail was, for example, if the pipe was in water, it would be -3 meters under the water. And then it grows 1, 5, 9, 13. So this snail is traveling at a certain rate. In example 1, you're asked to determine, is this particular table linear? Does this represent a linear relation? Well, in order to do that, we need to prove it by justifying our answer by showing our work. And that is, we need to do the delta. Delta table, delta time is equal to, let's find out, 0 to 3 is +3. 3 to 6 is +3. 6 to 9 is +3. 9 to 12 is +3. So, this whole entire thing has a value that is the same. So the delta time values are all the same. Next, we look at delta height. Delta height, those values, let's find out what those values are doing. So delta time, these values are all the same. That gives us permission to go to the other side and determine delta height. How are the height values changing? That is, delta height from -3 to 1 is +4. From 1 to 5 is +4. From 5 to 9 is +4. And finally, from 9 to 13 is +4. So these values are all the same. So therefore, we can make a conclusion that this particular table represents a linear relation because delta time and delta height values are the same. So delta time and delta height values are the same. Next part we need to look at is example B. What would the next value be in the table? So you need to be able to extend the table if required. So what would the next values be? Well, we can determine that by looking at the next pattern. That is, in the x values, what we're doing is adding 3. So 12 to add 3 gives us 15. Now on the other one, we have 13 plus 4 will give us 17. So the next value in the table would be 15, 17. Part C is determine the slope. So we need to determine the slope of this particular table. Because it's a linear relation, we can determine the slope. That is, slope is equal to y2 minus y1 over x2 minus x1, or another way that we learned it was rise over run, and another way we learned that was delta y over delta x. Slope can be represented by any one of these three ways. Well, for us, it makes sense to use delta y and delta x. Delta y is +4. Delta x is +3. So delta y over delta x, or delta height over delta time, is 4 over 3. Or we could use the coordinates. Let's say we use two sets of points, these two in the middle. We can determine the slope by writing 3, 1 upwards. So you notice I wrote 3, 1 upwards. That's this set of coordinates. Then we take the next set of coordinates, 6, 5, and we write 6, 5 going upwards. And then we draw, that's right, 3 lines. 1, 2, and 3. And we can do 1 minus 5, which gives us negative 4, and 3 minus 6, which gives us negative 3, which will equal, again, the same answer we had earlier, which was 4 over 3. Because the negatives, as you remember, the negatives will cancel each other out. So we'll have a positive value as our final answer. All right, let's look at the next example. In this table, what you'd be asked with the table is to graph the relation. So you'll be asked to graph the relation. So to graph the relation, you need to graph the x and y's, okay, in such a way that we get this nice big graph. So we will graph the relation, and we notice that all the dots form, that's right, a line. All the dots form a line. That line has arrows at the end of it, and so you will have arrows at the end of each of that line, at the end points, because this graph continues on forever and ever in both directions. And we can see that this table forms a straight line. And if you were to calculate the slope, don't forget, you would just rise from the leftmost point to the rightmost point. So we determined that the slope was, all right, let's see, 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6. 4 over 6 reduces to 2 over 3. So our slope is still correct. Is this a partial or direct variation? So the question is, which one is this line a partial or direct variation? Well, let's recap. A direct variation goes through the point 0, 0. So this pink line is a direct variation. That means the blue line must be, that's right, a partial variation. So direct variation always goes through the point 0, 0. Direct variation goes through 0, 0 always, and a partial variation does not go through 0, 0. So therefore, this is a partial variation because the line, the blue line, does not pass through 0, 0. Last but not least, for this example, you're asked to determine the equation of this line. And that's a hard thing to do at this point because you've never seen this before. Well, folks, it really isn't that hard because I've been building to this moment. That is, we need 2 parts to every line. The equation y equals mx plus b represents the equation of every line that can be used. Now, we have to understand what these variables and these letters represent. That is, m, y, and x remain in the equation. All slanted lines will always have a y and an x in its equation. Now, what we need to do next is fill in the m and the b. We need to find the slope, which we already did, and the y-intercept, which we can look in the table or see right here. The table, if you look up here at the table, you will see that 0 and negative 3 are the coordinates in the table, and 0, negative 3 are the coordinates that passes through the y-axis. That's right, m represents the slope and b represents the y-intercept. So if we plug in the numbers that we have, for slope, for example, is 4 over 3, x, and then our y-intercept is plus negative 3, okay, plus negative 3 gives us minus 3. Now, earlier I mentioned about the slope. I have to correct myself. When we were rising up to go across to the point, I wasn't paying attention to the scale of my axis. If you notice the scale of my axis, this is going up by ones. So this is going 1, 2, 3, 4. But then when we look along the x-axis, we notice that 1 is every 2 blocks. So it goes up 4 over 3. 1, 2, 3. And so the slope was 4 over 3, folks. And it was just because I wasn't paying attention to the scale. That's really important. Okay, so back to over here. The equation is y equals 4 over 3x minus 3. Okay, last but not least. To find the slope, we need to remember the following. So this is all just a recap of everything we've learned in this chapter. That is, to find the slope, we need to calculate m equals. M equals what? Well, rise over run, which is when you're given a graph, you go up or down and then run to the right. Or we need to find slope using a formula, y2 minus y1 over x2 minus x1, such as the following. If you have two sets of coordinates, you will put those coordinates upwards first, very important. You rewrite them upwards, 2, 3, and 4, 5. And then what we will draw is 3 lines. That is 1, 2, 3. And what that will give us is how to find the slope. 3 minus 5 is negative 2. 2 minus 4 is negative 2. The answer is 1. So the slope in this example would be 1. We use the formula y2 minus y1 over x2 minus x1. Next, what's important when we see slope is that it should always be in fraction form, unless specifically stated, like a rate of change. It must be a fraction and in reduced form. That means so that no decimals. Now, the last one for slope is delta y over delta x. We use delta y and delta x when we have a table of values. We use the delta x from the right side, delta y from the left, delta x from the left side, delta y from the right side to determine the slope. Now, to find the y-intercept, you look for where the graph crosses the y-axis. Wherever the graph crosses the y-axis, that is, when x is 0, the y value will be your y-intercept. So, one more time. 0b, we look for when x is 0, the y value, the b, will be our y-intercept. The b is the y value of the y-intercept. Finally, we need an equation of a line to represent this particular linear relation. So we always use the formula y equals mx plus b, where m stands for the slope and b stands for the y-intercept, and y and x is just the variables that are always found in the equation. All right, folks? Well, this is just a recap of everything we've learned in this chapter. Have a numerical day.